Okay, good morning everyone. I'm Maximilian Stilz from the University of Freiburg, and I'm going to talk about yet another pantographic structure, a three-dimensional one called the pantographic ortho-block. I'm going to talk about the continuum and the numerical implementation, and I did this work together with Simon Eugster from the University of Stuttgart. Okay, so I think I don't have to go into detail what pantographic structures are, but just so that you remember, we have two families of fibers, and they are interconnected somehow by something we call pivot. And my motivation for this new structure was to simply bring the pantographic behavior also in the third dimension. We just saw the pantographic block. It still has the pantographic sheet. In the third direction, we still have a first gradient material. And I wanted to combine this into a material that has second gradient behavior in all directions. And so I naively just glued orthogonal and parallel pantographic sheets together and see if I could get a material that makes any sense. And it did work out. And it has a unit cell that idealized looks like this. So we have four families of fibers, and they are interconnected at one point. We call also pivot for simplicity. And always two families of these fibers are in one plane. So we have four fibers and two planes. So what does this point P look like? So this interconnection. And I mean, we can also realize it as some sort of maybe stiff connection or whatever. So it's kind of this double pivot. So just two pantographic unit cells also glued together in the middle. But we can also come up with maybe different sorts of interconnection. So also especially interesting is connecting it with rotational joints. So that we have four rotational joints at the end of the pivots connected to the fibers, and we also tried to already print this. And I can maybe just give it around, maybe you want to have a look. You will see that we still have issues printing this material. There are still supports inside, so we were able to print this with somewhat perfect pivots, but the problem is, of course, in 3D printing we need supports. We have here basically a completely loose part. So we need print supports in the structure, but they are hidden so deeply that we're still struggling to remove this. If you have any idea how to remove them, please let us know.
This is your job.
Yeah, but maybe somebody can do it for me. Okay, so I'm now introducing the continuum model. The approach is similar to what we've seen already for sheets and also just right now for pantographic blocks. I'm assuming here a three-dimensional body, and I assume a heading of fibers. So I have these four fibers that are in every material point somehow represented in this continuum. And I have a placement function and my deformation gradient, and I hope that through this embedding I can represent the deformation of this unit cell or of these fibers. So I start with a reference configuration where every fiber is represented by a triad. So it has a tangent, a normal, and a third direction. We need a triad, of course, because we also want to consider the cross-section of these fibers. And always two fibers are embedded, as I mentioned, in these pantographic planes. So we also have two planes. So we say that fibers 1 and 2, they belong to the plane family A, and fiber 3 and 4 belong to a plane family B. So A and B are always orthogonal in the reference configuration. Yes. Okay, and then we also define a normal of these planes, and in the reference configuration, they always coincide with the normals of the fibers. Then in the deformed configuration, we consider that the tangent of every fiber is then deformed through the deformation gradient to the tangent of the current configuration, and then we can define a unit tangent. From these unit tangents, we can calculate the normal of these pantographic surfaces in the deformed configuration. Again, they're like these embedded surfaces. And then we introduce a kinematic constraint. This is debatable, could be changed, but we consider that this connection between the two fibers is in that way that their normals also coincide in the deformed configuration. So this is just basically a constraint of the orientation of the cross-section of the fibers. And then we define the third direction of every fiber. We call it here the bitangent because it's still, because of this constraint, it lies in the tangent plane, in the plane of these pantographic surfaces. So the deformation measures are then just retrieved considering like a curve in a three-dimensional space. So we can calculate the change in length of this curve, and we can, through the gradient along the fiber of the tangent, we can also define the curvature. We project this curvature in two different planes. So we have a normal or in-plane bending, so bending in the pantographic surfaces, and an out-of-plane bending, so out of the pantographic surfaces, and finally also the torsion as basically the rotation of the cross-section. Then additionally, we need to address the interconnection of the individual fibers. We do this here in a very simple approach. We just consider three angles. So the angle between two fibers in one plane. So this is the same as we talked about before, the pivots, the role of the pivots. Also like in the pantographic sheet or the pantographic block. But we also need to consider the interaction between the sheets. And here we introduce another angle we call gamma C, which is the angle between two pantographic sheets in a plane. So this is an in-plane and an interplane shear. Then we propose a energy density quadratic in all these terms. So we have, for the fibers, elongation, we have bending, and so bending and torsion, and for the pivots, we have these two shear terms. So taking the first variation of this internal energy density, we can retrieve a formulation of the vertical work functional for a second gradient elastic continua. So they coincide. We don't need to propose this. The result is a second gradient elastic continua. We already saw most of it also in the talk yesterday by Professor Fedele. So here I just call G the gradient of F. We have the Piola-Lagrange stress and the Piola-Lagrange double stress. So P and blackboard P. And if we look at the contributions of the deformation measures, we see as expected that the second gradient terms here, they only come from bending and torsion of the fibers. So all other contributions are still first gradient contributions. We also want to have a look at the external work, so that we can consider what kind of boundary conditions our material can accept. And I mean, we can derive through some integration by parts. We can arrive at these terms that we have, like in the classic first gradient continua, body forces and surface traction. But we also get these new kind of boundary conditions, surface double forces and line forces. And from this we can also then get our equilibrium equations to see, okay, what boundary conditions my material can accept. Because even though it's a second gradient material, I'm not sure if I wrote that in the title, but it is still an incomplete material. So we have some missing contributions. So with these boundary conditions, we can check, and we find that first we find some zero energy modes for certain assumptions. So if we assume perfect pivots, so if there's no interplane shear, no shear in the pivots, we find this zero energy mode, this floppy mode, and so this is the floppy mode that would also be present in the material I just handed around. And we could also imagine another kind of floppy mode, which in theory should be possible also to print, but we're still trying to construct this. Then we would also have a floppy mode in intershears, an interplane shear. So if the planes could be rotated relative to each other, there would be another floppy mode. And as I mentioned just now, it is a gradient incomplete model. So for certain configurations, we find that not all kinds of these new boundary conditions can be applied. So that some double forces or line forces, depending on the configuration, cannot be fulfilled. So we have to be careful with that. Now for the numerical implementation, we chose to do it in the framework of isogeometric analysis. And so that afterwards I can show some simulations. We used our own in-house finite element code based in Python. We used the B-spline discretization because for the second gradient materials we need at least C1 continuity if we don't want to use a double field method or anything, if you want to use just one field, because we only use displacement as degree of freedom. We don't have a rotation field or anything. It's only displacement. So the deformation gradient in the discretized deformation gradient is defined through the generalized positional coordinates and the basis functions, a derivative of the basis function with respect to the current configuration. And its gradient, again, is just the derivative of these basis functions. So And in our code, we structured our code in that way, so we could, in general, introduce any kind of second gradient material. It's not just specified on this one. So you just need to know the structure of your first and second pure Lagrange tensors. And if you don't want your code to be very slow and avoid numerical derivation, you also need, for the tangent stiffness, because we use a classic Newton method to solve our problem, you also need the derivatives of the pure Lagrange tensors with respect to the deformation gradient and the gradient of the deformation gradient. And I mean, this here is a 6 times indexed object. So if you do this numerically, it gets very, very slow. For the showcase simulations, I chose a cuboid configuration with the length of 70 millimeters on the short side. The stiffness factors are based on beam properties, and I compared it directly with a Timoshenko B model. The B model is also in the same software, so we can, I could easily compare these two. And I will show like a superimposed. I will show it superimposed. So the continuum model and the gray part is another beam model. They're not simulated together. They're simulated separately, but then they're combined to see if they show similarities, hopefully. yeah, the reference configuration. Otherwise, it shows so it's just the sheets in this plane, and so this is the XY plane, and sheets also in the YZ plane. So let's see if my videos work. Yeah, they do work. So this is the floppy mode. Works quite well in both cases. Then I have a traction test. So a simple clamped tension test. And already what we can see here, one interesting property of this material is that it is semi-oxidic. So when I clamp these ends and pull, then here it gets shorter as expected, but here it gets wider. So it has 1 negative and 2 positive Poisson's ratios. And a slightly more complicated boundary condition, a twist and a pull, and yeah, we can still see at least at first glance the B model and the continuum model coincide quite well, and also still because of the traction, also here the semi-oxidic effect is still in place. So I don't only have pretty pictures, I also did some direct comparisons. I compared the individual energy contributions from the B model and the continuum model to see if they represent each other well. So on the left you can see the clamped extension test. The dashed line is the B model and the solid line is the continuum model. And I can see here that for the extension, at least at the beginning, they coincide quite well. Then there is a derivation at the end. I first thought it is due to buckling, but because this is the extension energy that diverges, I'm not so sure anymore. So here I have to go into the details a bit more. On the bottom, you can see this is in absolute numbers for an extension test on a 20 centimeter specimen, 50 centimeter displacement. The mean difference in displacement is about 1 millimeter, so yeah, quite well. And it's a lot better in the clamped torsion test. There the energies, the single contributions, extension, torsion and bending and geodesic bending, they coincide nearly perfectly. And also for the absolute displacement in this 90 degree torsion, there is a displacement difference of less than a millimeter. Okay, so to conclude, we designed this three-dimensional metamaterial with a pantographic substructure. It is semi-oxidic, has possibly 2 zero-energy modes. At least the model is an incomplete second gradient material. We found very good kinematic agreement with the beam model, and we developed a isogeometric analysis for three-dimensional second gradient continua. But what is to do is experiments, and that is where we are still struggling with the printing right now. And what also really interests me is these new kinds of boundary conditions, so gradient boundary conditions and line forces, especially also experiments in this region would be very interesting. And also we have to maybe look into alternative continuum models. For example, I did not consider the dimensions of the pivots in my model. I assumed that they are zero, that they were very, very small compared to the beam length, and so this has still to be considered because the unit cell itself is chiral when I introduce this distance, and I think this would also influence the kinematics. Yes. Okay, thank you.